In example 5, we're given the joint density function f of y1, y2 is e to the negative y2, and we're given that on a particular region. I think I better start by graphing that region, because otherwise there will be some confusion. So there's y1 on my horizontal axis always. There's y2. I think that might have run slightly off the slide, so let's move that in a little bit. And we're told that they both go from 0 to infinity, but y2 is always bigger than y1. So let me graph the line y2 equals y1. And now we're looking at this region sort of above that line. Now, this is the same setup that we had in one of the examples on the previous lecture. So let me give you a reference for that. This was in the lecture on marginal probability. Marginal probability. And it was example 5 in the previous lecture. So you might want to go back and look at our solution to example 5 in the lecture on marginal probability, the previous video. If you just scroll up here, you'll see it. It's the same example, but we're calculating something different. What we did there was we calculated the marginal density function. We calculated f1 of y1. The way we calculated it was by doing the integral on y2 of the joint density function fy1, y2, dy2, and the answer we got there was e to the negative y1. There was a little bit of work to getting it, so I'm skipping over some of those details when I talk about it now. So if you want to go back and check that out, or if you want to redo the integral, then you'll see where that comes from. In today's example, what we're going to figure out is the expected value of y2 given that y1 is equal to 5. So let me show you how we're going to calculate that. We're going to use our formula for conditional expectation. Let me see if I can graph this quickly. Y1 is equal to 5, so I'll just arbitrarily say that that's 5. And so that means we're on the line y1 is equal to 5. So there is the line y1 is equal to 5, and that's the line that I'm looking at, and I want to figure out what the expected value of y2 will be if I know that I'm fixed on that red line. So I'm going to use the formula for conditional expectation. That is the integral on y2 of, here's the new part, the new element is y2 times f of y2 given y1. y2 conditioned on y1 dy2. So the new element there is that y2 in order to calculate the conditional expectation. Now that means I have to figure out what f of y2 conditioned on y1 is. So let me calculate that over on the side here. F of y2 conditioned on y1. By definition, it's f of y1 comma y2 divided by the marginal density function f1 of y1. And so in turn, f of y1, y2, where was that? Oh, that's e to the negative y2. That was given in the stem of the problem, e to the negative y2. And f1 of y1, that was what we figured out in example 5 of the previous lecture, of the marginal probability lecture. So that's e to the negative y1. And so if we put those together, e to the negative y1, if we flip it up to the numerator, that'll be e to the positive y1. So e to the positive y1 minus y2. So that's what I'm going to plug in there. Now, what's my range on y2? Well, if you look at the range on y2, it's all the range of this red line. So that red line starts at y2 is equal to 5, and it goes on up to infinity. So my range on y2 is going to be y2 equals 5 to y2, well, I'll take the limit as it goes to infinity. And now I'm integrating y2 times e to the y1 minus y2 dy2. Now, I don't want to see a y1 in here. I want to be integrating with respect to y2 because I need to get an answer in terms, a numerical answer, and I'm integrating only with respect to y2. So I'm not comfortable with that y1 in there, but I'm given that y1 is equal to 5. So I'm going to plug in y1 is equal to 5, and so I get the integral. I won't write the bounds right now. y2 times e to the 5 minus y2 dy2. And that's much more reassuring now because I have only y2's in there. I know that if I integrate this with respect to y2, I'll get a numerical answer. Something I can do here is I could pull out e to the 5th. So that's e to the 5 times y2 times e to the negative y2 dy2. And that's a slightly unpleasant integral. I'm going to have to use integration by parts on that. Let me do a quick integration by parts. I'm going to use tabular integration. It's sort of the cheater's way of doing integration by parts quickly. y2 e to the negative y2. If I take derivatives on the left, the derivative of y2 is 1, derivative of 1 is 0. And the integral of e to the negative y2 is negative e to the negative y2. The integral of that is e to the negative y2. Draw my little diagonal lines and put a plus and a minus there. And this is e to the 5th times negative y2, e to the negative y2, multiplying down the diagonal lines, minus e to the negative y2. So that was integration by parts, borrowing some techniques from Calculus 2. If you're a little rusty on your integration by parts, guess what? We have a video lecture series on College Calculus Level 2. It's hosted by none other than Will Murray. It's right here on Educator.com, and you can figure out, you can review your integration by parts if you're a little rusty on that. But in the meantime, we're going to plow forward with the probability, and we're trying to integrate this from y2 equals 5 to the limit as y2 goes to infinity. So this is e to the 5th. Now, I see I have e to the negative y2 here. If I plug in infinity, that's e to the negative infinity, and even though that's multiplied by infinity, if I did a little L'Hopital's rule on that, it would still go to 0. And e to the negative y2 is still 0 when I have y2 going to infinity. So both of those terms drop out. And then I have the terms for y2 is equal to 5. So plus 5e to the negative 5, plus, I'm putting pluses in here because I'm subtracting negatives, e to the negative 5. And I see I've got e to the 5 times e to the negative 5. Those cancel out. And this is 6e to the negative 5 times e to the negative 5 cancels out. Gives me a very nice answer here. It's just 6 is my answer. That's my expected value of y2 given that y1 is equal to 5. So that's what I just calculated. The expected value of y2 given that y1 is equal to 5. If somebody tells me that y1 is equal to 5, that's going to be my guess for what y2 is. Now, that's really the end of that problem, but let me recap the steps here. First, I looked at the region here. y1 and y2 go from 0 to infinity, and I just graphed it. So I graphed that up here. It's this blue triangular region here. The important thing to notice there is that y2 is bigger than y1, which is why I have the region north of the line y equals x. And then I also noticed that we were told that y1 is equal to 5. So I went ahead and graphed y1 is equal to 5. It's this vertical red line here. And since we're calculating conditional expectation, I'm going to use the conditional expectation formula, which we learned about on the third slide of this lecture and sort of the preamble to this lecture. And you integrate the conditional density formula, but you put this extra factor of y2 in there because it's the conditional expectation. So that sort of comes from this term right here. That's where we get that y2 from there. Now, what about this f of y2 conditioned on y1? Well, that's something we have to calculate as the joint density function divided by the marginal density function. And the marginal density function was something that we figured out back in the lecture on marginal probability. We did this problem, or at least that part of this problem, back in example 5 of the previous video. So just go back, scroll back and look at example 5 if you don't remember where that comes from. But the answer for the marginal density problem, for the marginal density function, was f1 of y1 is e to the negative y1. Drop that in right here for f1 of y1. The numerator here, f of y1, y2, that comes from this given function here. So that's where that comes from. And then I simplified that to e to the y1 minus y2. And then I plugged that whole thing back in here, back into this integral. And I didn't like the fact that there was a y1 in there. The reason I didn't like it was because I'm integrating with respect to y2, and I want to get a number at the end, so I have I don't have any way to get rid of that y1. Oh, except to remember that I was told that y1 is equal to 5. So that's where I plugged in 5 for y1, which was kind of nice because it made it into e to the 5 times e to the negative y2, and I can pull it right out of the integral. And now I have a nice little integral in terms of y2. Fairly nice little integral. It's something that I have to use integration by parts for. So if you're rusty on your integration by parts, here's sort of the quick and dirty way to do an integration by parts for this kind of problem. If you really want to practice integration by parts, check the Calculus Level 2 lectures here on Educator.com. You'll see a whole lecture on Educator.com on integration by parts. And so you can get up to speed on that. So here's what the answer gives me from integration by parts. And then I plug in y2 going to infinity, but that kind of kills both terms. If you do a little L'Hopital's rule, you'll see why that term gives you 0. And then I plugged in y2 equals 5 to both terms. That simplified down to 6e to the negative 5, which very nicely canceled with the e to the 5 and gave me just 6 as my expected value. So that wraps up this lecture on conditional probability and conditional expectation. We're going to keep using some of these same concepts in the next lecture, which is on independent random variables. We'll see how that's connected to some of this. This is part of the chapter on bivariate density functions and bivariate distributions, functions of two variables. And that in turn is part of a larger lecture series on probability here on Educator.com. Your host all the way is Will Murray. Thanks very much for joining me today. We'll see you next time.